Hello, everybody, and welcome to Galvanic Sulfur Recovery Unit application training session. My name is Parisa, and I'm the Senior Portfolio Manager with Galvanic Applied Sciences. Today, I'm going to provide a quick overview about sulfur recovery units, and then I will discuss some of the key applications in sulfur recovery plants, such as the acid feed gas as well as the tail gas, sulfur pit gas, and the tail gas treating unit applications. Okay, let's get started by a quick overview about the SRUs. So the whole idea of any SRU is to convert the hydrogen sulfide during the class process to elemental sulfur. This can then be used to produce sulfuric acid, fertilizers, medicines, cosmetics, and much more. Where does this matter? In lots of processes, such as refineries, natural gas plants, coke oven plants, in all of them, there is an SRU unit possibly. So it is very important to convert as much as possible of that H2S to elemental sulfur to make sure that we increase the plant efficiency as well. We can minimize the environmental release sulfur compounds. Now, this one here is a generic diagram that is basically showing the whole process. At the start, the feed gas or the acid gas is entered. And basically at the front end of the process in the reaction furnace, and then air also gets added to it. The class chemistry consists of two types of reactions. One is a thermal reaction, which happens in the reaction furnace, where the substoichiometric amount of the oxygen is being added to convert 1/3 of the H2S to SO2. In the next step, what happens is that it's a catalytic step, so the rest of the H2S reacts with the produced SO2, basically to make the elemental sulfur. Now, in the modified class process, the catalytic step can be repeated over and over to further increase the efficiency. What is very important is to make sure the amount of the oxygen that is being added is enough to keep a ratio of 2:1 between the H2S and SO2, and that's what's highlighted here in this reaction as well. So it is usually more convenient to talk about the air demand rather than the ratio. So if too much oxygen is added in the first step, then the air demand signal becomes positive. And if it is not enough, then that air demand signal will be negative. Now, the air demand control basically is done mainly through the feed-forward or the feedback analysis. So there are two options, and then we'll discuss them during this webinar shortly. This one here is a graph that shows the SRU efficiency loss versus the air demand signal. So in an ideal case, the air demand is 0, as you can see in the center. On the right side, you see the air demand is positive. That basically shows that there's too much air added here, so they have to cut the air. On the left side, you see we're on the negative side. So that means the air demand is negative. It means that more air is basically required for better efficiency in this reaction. All right, let's just have a quick look at this table here. So this table basically lists some of the main applications in the SRU. One is the tail gas application. This specifically refers to the air demand control at the end of the sulfur recovery stages after the last condenser. So we also will discuss in this webinar one of Galvanic's patent applications, which is the double air demand or DAD, which is a new control strategy to further enhance the air demand control at the SRU plants. Next one is the acid feed gas in this table. That refers basically to the air control at the front end of the reaction furnace. We also have a pit gas application in the sulfur recovery plants. And the focus of that application is controlling the H2S and SO2 in the headspace above the sulfur pit, mainly for the safety purposes. We'll talk about the tail gas treating units, or the TGTUs. That refers to a specific process after the SRU to convert the tail gas to H2S so that it can be sent back to the SRU again as the feed for producing more and more elemental sulfur. All right, let's get started with the feed gas applications. As mentioned earlier, so there are two ways to keep the control on how much air actually goes to the process. One way is to analyze the tail gas at the end of the process, which is pretty accurate. However, the problem is that that's limited to the process lag time. So if there is any upset condition in the process, or for example, in the feed gas, that basically where the feed gas composition changes abruptly, for example, it takes time for the analyzer to analyze that at the end of the process. Therefore, it will not be possible to respond right away in a timely manner. So during the feed-forward analysis, or in the feed acid gas analysis, however, the composition of the gas can be analyzed upfront before it actually goes to this reaction furnace here. So rough estimate about how much air is required to run the chemistry in the furnace can be calculated ahead of time. So this analysis basically accounts for about 90% of the air control in the SRUs. The main component in the feed gas that consumes majority of the air is H2S. Also, depending on the feed gas composition, there might be other chemicals in the stream which can use some of the air. For example, one of them is the hydrocarbons. Okay, so for the feed gas analysis, Galvanic basically offers the 962AGX analyzer, which measures H2S based on the UV technology on the feed gas before that gas goes to the reaction furnace. This analyzer has a sample handling panel, as you can see on the left side here in this picture. That includes the oven cabinet as well, which includes the oven cabinet as well. So that's the oven cabinet you see in this picture. The cell is located in the oven cabinet. The control cabinet is on the right side, and that includes all of the electrical components and the parts that are required for the analyzer operation. So before the sample goes to the cell, it also goes through a filter that is inside that oven cabinet just to remove any particulates that might exist in the stream. Again, the main purpose of the acid gas analysis is the proactive air demand control or air control based on the H2S measurement using this system. That's important to avoid going through situations that are not really appropriate for the reaction furnace. So basically any upset condition that can affect how much air is going to be used. Another application we talked about was the tail gas application, or tail gas analysis, or that's known as the air demand as well. So the most important analysis in the SRU basically is the tail gas analysis. This allows tight air demand control to meet the expected ratio for the H2S to SO2. That's through a fine-tuning of the trim valve, which accounts for about 10% of the air adjustment in the whole SRU plant. So having a good idea about the air demand, the operators can decide on how to adjust the air through the trim valve, just basically to provide a more accurate amount of the air as required for the reaction furnace. So ideally, a combination of some sort of feed-forward control that accounts for the 90% of the air, and the feedback control that accounts for the 10% of the air could provide a really good air control all the way through, which results to a better overall performance at the SRU, because we can get a control of both up front and also all the way to the back of the SRU air demand control. All right. Now here, I want to spend a few seconds talk about some of the main challenges that we see most of the times in the SRU, basically in the terms of the analysis. One of the main challenges is plugging issues that affects what analyzer can see and what kind of results we can get. So when we talk about sulfur and SRU, we always have to consider the chance of the plugging and condensation and make sure that we have a plan in place to avoid it when designing the analyzer and the sample system. Sample lines are one common area of the pluggings and in the plans. They also add more to the analysis time, which is not pleasant, specifically when we are at the very end of the plan, and the time efficiency is really critical at that point. The longer the sample line, so the more chances of plugging exist as well. And these are some pictures that give you an idea of some sort of kind of problems that are seen in the plans. Another issue is the major component in the stream that should be removed before the analysis, which is the sulfur vapor. Sulfur vapor can absorb strongly in the UV, which is a technology being used in the tail gas, and can have a significant effect on the accuracy of the H2S and SO2 and therefore the air control measurements. So there are different ways to remove the sulfur before it actually goes to the cell. Such as condensing in the probe or removing it in the demister or any other similar method. Obviously, the sooner we remove it, the lower the chances of the condensation or plugging will exist. Also, there will be less troubles to maintain the heat integrity of the whole path until the sample is transferred to the cell. So unlike some other designs, the way that Galvanic removes, or brimstone removes the sulfur vapor is right away in the line in the probe. Therefore, there is absolutely no sulfur that's carried to that analyzer that has a chance to do any condensation or plugging. So that's a really big advantage of removing the sulfur in line. In terms of the hydrocarbon breakthrough, that's another challenge that some people see in their plants. So basically, unburned hydrocarbons can contaminate the closed catalyst with soot and can result in the operational issues. For example, replacing expensive catalyst. A main indicator for hydrocarbon breakthrough or possible catalyst problems basically is measuring the COS and CS2. So under the normal situation, the COS and CS2 are supposed to be hydrolyzed to H2S in the first catalytic step. As can be seen here, in this spectra here, the broadband spectral analysis that is used in Brimstone Analyzer gives the opportunity to scan and analyze 530 pixel windows in the full spectrum rather than a few selected wavelengths. Therefore, that provides the opportunity to measure more species than only H2S and SO2. For example, we can analyze COS and CS2 with no interferences. So that's another beauty to have all of the measurements and components in one package. So being able to analyze every individual species with no extra cost or any other limitations when you're using the broadband spectrum. All right, another operational challenge at the plant is the installation issues. Some of the tail gas analyzers, they are limited to specific sample port sizes, which require the pipeline modifications. Some might need utilities, for example, that are either not accessible in the plants or are considered really high cost to supply. For example, one common one that we often hear is the high pressure steam. Some are limited in terms of the ambient temperature ranges. Some might require more space compared to what exists already on the process pipe. So to address all of the issues I mentioned, brimstone analyzer can adjust to different pipe sizes. It does not require any sort of high pressure steam because the whole oven is completely upgraded to electronic version in all of the models. It also comes in different flavors. So if the single unit does not fit on the process pipe, the split version can be offered. And the way that works is the oven cabinet is installed on the process pipe, and the electric or electronic cabinet can easily be installed farther where there is more space available. So again, only in one single design, all of the main issues regarding all the installation, everything else we talked about is addressed. All right, so how do we make the measurement for the tail gas or for the air demand? The 943 family is the most common version of the brimstone tail gas analyzers. It is a UV-based analyzer and can measure all H2S, SO2, and COS and CSO components in again one single unit. And again, the main benefits are optimizing the ratio of the H2S to SO2, also the air demand control and the control of catalyst conversion efficiency all together. Okay. So to summarize some of the main features and the benefits of the brimstone tail gas analyzer, the chances of plugging are minimized as the sulfur condensation happens in the process line. So nothing that does not require analysis goes to the analyzer at all. The analyzer is a closed couple analyzer, therefore there is no sample lines here. So chances of plugging, condensation, and all of that due to the sample line are none. Also, it's a faster measurement because the response time is going to be faster for the closed couple model. Utilities costs are minimum and no specific process modification is required at all. So also the full spectrum analysis that we talked about allows the measurement of all of the four species, H2S, SO2, COS, and CS2 in one single unit, and then we're done. All right, now that we know the tail gas analyzer family and how that works, I want to introduce the double air demand or DAD applications here. So far, we talked about the tail gas analysis to control the air demand, which is accurate, but also limited by the process lag time. So accuracy is wonderful, but limitation by the process lag time could be an issue. Also, in the case of the hydrocarbon breakthrough, the feedback control cannot efficiently and in a timely manner detect and basically respond to the problem if there is a change in the composition. We also talked about the feed-forward analysis of the feed gas before it goes to the reaction furnace. So there are several methods available to analyze the feed gas composition. Some of them, such as the GC, can provide a detailed analysis of the species. However, it takes a few minutes to do all this analysis, which is a limitation because it exceeds the time that is required to detect and respond quickly during the upset process in the SRUs. Other methods such as UV, IR, TDL, and some others can exist as well, which are either limited in terms of the potential interferences or are matrix dependent, so that's another limitation, or might require complex installations that have really sensitive optical design for the feed gas stream applications. So far, there is no complete solution in the market that can actually address all of those measurements in the feed gas with no limitation and with a high degree of accuracy. So they all have their own limitations. All right, so between the different methods of controlling the air demand, one solution is to measure the air demand right after the complicated reaction furnace chemistry to make sure that none of the analysis limitations and concerns and everything we mentioned in the feed gas section exists. Double error demand, or the DAD patent application, is a new control strategy by Galvanic Brimstone that enables the entire SRU air control in only one package by a combination of the trim valve control using the input of the TLS analyzer after the last condenser, and the main valve control using the input of a similar analyzer right after the first condenser. So this picture is showing where the analyzers will be located. One is the typical after the last condenser, like the tail gas, and in combination with another one right after the first condenser in a package. After the first condenser, we are still very close to the front end of the plant, so we can analyze and adjust for any upset situation if it happens very quickly and in a really timely manner as required for this analysis, without being affected by any of the unpredictable feed gas issues that could happen before or during the reaction furnace. So it's a very smart design how we bring this package together. Another operational advantage of the DAD system is that if one of the analyzers fails for any reason, the plant can still be controlled automatically using the other analyzer, which is a much better control than having to use the manual control, obviously. All right, some of the typical questions that might be asked regarding the DAD are that, do we need a bigger probe or a bigger heat exchanger or higher cooling capacity? The answer to all of these questions is no. In fact, the conditions are more favorable upstream. So despite a higher sulfur vapor and the temperature, water vapor is less upstream, and less water content can actually reduce the required cooling capacity for the sample probe. In fact, the average cooling capacity is almost equal for both sample points. So we might just need to adjust the cooling airflow in the probe slightly to lower down the temperature to get rid of all of the condensed sulfur before going to analyzer, but everything is the same as the unit that is used in the TL gas analyzer. So very straightforward and robust design. All right, another application that we see often in the SRUs is the sulfur pit analysis. It is specifically analyzing the headspace above the sulfur pit where the sulfur is actually stored. So that vapor space above the sulfur pit often includes some H2S as well as SO2. So it is very important to keep the H2S below the lower explosive limit, which is about 3 to 4%. Also seeing a significant amount of the SO2 is an early sign of the sulfur fire in the sulfur pit. So the way that many of the plants may be dealing with this issue is just through purging or souping with the air, obviously. The sulfur pit can also contribute to SRU's total SO2 emissions as well. So in order to reduce that SO2 emissions, sometimes the operators reduce basically do some creative, designs and temporary solutions. So sometimes the operators reduce the pit vent gas flow to compensate for basically that high SO2 emissions. This causes some obviously blockage in the pit vent gas, which risks increasing the H2S levels as well. Okay, also having a reliable system to analyze these species, as I mentioned, so that can help. We can minimize the utility costs, as well as the equipment, sulfur pit damage by reducing the chances of having a fire. So this is all advantage for the safety mainly. How do we measure those? The Brimstone model 202 SPX that you see in this picture here is a reliable, again, UV-based analyzer. That's extremely valuable for plants to have an analyzer that can measure both H2S and SO2 to make sure that the H2S is always below the LEL and the SO2 is below what is required to cause a sulfur fire in the sulfur pit. This makes it very reassuring that the plant safety as well as the operator's safety is addressed with a good certainty in the plants. All right, so far we discussed the main applications in the SRU, including the feed gas, the tail gas, the feed gas applications, and the double earthman application. Now, some of the plants follow with a tail gas treating unit or TGTU after the SRU in order to further increase the recovery efficiency. So here is a list of some of the TGTU processes. The most typical TGTU process is SCOT, which is the shell cloth off gas treatment. It is an amine-based treating unit, which includes a reduction reactor to basically reduce all of the sulfur components in the tail gas to H2S by reacting them with H2 or hydrogen in the presence of COMO catalysts. The gas is then sent to a quench tower and from there to an amine absorber tower so that this H2S is absorbed with the amine. The sweet gas leaves the tower at the amine absorber overhead, and that has as less amount of H2S as possible. The amine that includes that high level of H2S then goes to a regenerator unit that regenerates the amine, and separated H2S then goes back all the way to the COS process and SRU to further convert to that elemental sulfur. So this here is just a list of some technologies being used for that recovery of the H2S and the amine absorber units, and some other technologies basically that exist for this cleaning process. All right, so here what we see here is basically a diagram that shows how this tail gas treating unit, or that's an SCOT example, works, again back to the quench tower as well as the SCOT absorber and how the whole regeneration happens in the systems and in this units. So in terms of the applications, basically what happens here is that there are different points in the TGTU to analyze. So one of the popular points to measure H2S is at the outlet of the quench tower. So H2S is basically measured here at the quench tower overhead for the material balance purposes in the SRU, and also to quantify the amine load. So it is typically in the range of 0 to 5%, and the analyzer we use here for this measurement is again a UV-based analyzer. It's called the FPA 4100. That analyzes H2S accurately at this point. The overhead of the amine absorber unit is basically includes the lean H2S. That is important also to analyze before sending it to the incinerator, as it can contribute to emission, obviously. So measuring H2S at the amine absorber overhead can provide good information about the amine absorber efficiency. So the amine efficiency is low if too much H2S is released, and it is high if we see much lower amount of the H2S here. So basically, these are two of the main applications here that can be measured with this analyzer. So here for the amine absorber, we use the acrylics. It's a laser-based technology. There are more applications here as well in the TGTU. And at this point, I'm going to pass it on to Steve, who will discuss more applications in the tail gas treating units. Steve?
Thank you, Carissa. Hi guys, my name is Steve Studowski. I'm the platform manager for the liquid analyzers here at Galvanic. Now we're going to talk about the amine sweetening process in the tail gas treater unit. Here we have a detailed flow diagram highlighting the amine sweetening process. Various amines are used depending on the application, such as methyl diethanolamine. Fresh or lean amine becomes rich after it absorbs H2S from sour gas in the absorber. Rich amine continues to the regenerator where it strips off the H2S. The newly lean amine is pumped back to the absorber and the cycle continues. When amine, a base, reacts with H2S and acid, the reaction creates a salt or anion. The reaction efficiency is based on maintaining Proctor chemistry conditions. Amine is replenished in order to ensure optimal alkaline conditions. Determining when to replenish amine is based on the amine strength or buffer capacity. If the pH drops too much, H2S removal becomes inefficient and side reactions can occur. Side reactions occur when the amine falls out of pH specification. This causes the formation of various heat-stable salts to form, which remain in solution. Heat-stable salts can form when there are issues with makeup water or treated streams. This impacts the process by accelerating corrosion, causing plugging and foaming. Heat-stable salts also cause incorrectly overestimating amine strength during analysis. The best way to measure is using potentiometric acid-base titration with a pH electrode. This allows you to truly determine the buffer capacity and correctly adjust dosing as needed. Inline pH sensors are often used as a proxy for monitoring amine strength. However, pH is a poor dosing control strategy since it only determines acid or base. Solely relying on pH leads to unexpected swings, and the probes can easily foul. The most important measurement for amine sweetening is the amine strength. If the amine value is too high or too low, upsets occur, which negatively impacts the process. Replenishing amine is expensive, so operators want to recycle the amine as long as possible. Other than amine strength, there are other components that should be monitored. Physical property changes, such as color, can also indicate process upsets. High metallic content or suspended solids accelerates corrosion. Heat-stable salts form side reactions and can also cause problems. Online wet chemistry analyzers can be used to monitor the liquid amine chemistry. Multi-parameter systems measure both amine strength and H2S loading. Multi-stream systems can monitor both lean and rich streams. Several other compounds can be measured utilizing different analyzer configurations. Galvanic's AccuSeries analyzer monitors amine following an approved ASTM method. Our analysis sequence guarantees plus or minus 2% of full-scale accuracy and repeatability. This is our third generation wet chemistry analyzer, marking 30 years monitoring amine. Our robust sampling system and sample conditioning minimizes maintenance. Online turbidimeters and photometers can measure suspended solids and color. Configurations are available to monitor suspended solids and color using one transmitter. Online viscometers can measure viscosity. These physical properties can be useful indicators for process efficiency. Galvanic's Monotech line of analyzers monitors both suspended solids and colors. We use a dual wavelength measure for color, which eliminates turbidity interferences. We use a near-infrared method for TSS, which can handle solids up to % levels. Galvanic's Viscosite uses a torsional oscillation method to measure viscosity. All these methods guarantee plus or minus 2% performance. Thank you, and now I'll hand things back over to Parissa.
Thanks, Steve. So back here again to some other applications in the SRUs. Another interesting application for the SRU is in the coke oven plants. And I mentioned that briefly at the beginning for the intro about the SRU. Let's have a quick look about this application. This one here is an overall overview about the whole coke oven plants. What we want to focus on is this side here unlike the typical class processes, coke oven plants often use the monoclass process. In this process, the kiln is positioned horizontally. The process gas cooler and condenser are mixed. There is also only one reactor or a catalytic bed in this plant. And this is basically a simplified diagram as you see here for this process. This shows where the tail gas analysis opportunity exists. So basically, coke oven plant can be another area for the focus for this sort of applications. All right, so again, as a brief conclusion here in this webinar, we tried to focus on discussing the SRU plans and all of the main applications that are more important in these plans, what to measure and how to measure them, as well as the ones that are relevant to the TGTU units and how Galvanic can support these applications with a high measurement certainty due to 40 years of field-proven experience in the SRU and TGTUs. So Galvanic offers basically rapid return on investment to optimize the air demand control, increase the SRU online time, as well as minimizing emissions, and most importantly, provide a high level of operation as well as the plant safety in general, which is the #1 when working in the SRUs. So this one here is a quick list of our sales team, as well as the product technical support. So please feel free to reach out if you have any specific question, if you would like to discuss any application or opportunity. With that, I would like to thank you all on behalf of myself, Steve, and the entire Galvanic team for attending this webinar. Please follow our website and our LinkedIn page for updates regarding our upcoming webinars. And with that, thank you again, everybody, and have a great time.